57 kilometers. That's how long it takes to drive across Switzerland, north to south. But today, a freight train carrying European goods doesn't drive across Switzerland. It drives through it. Beneath 2,150 meters of solid alpine rock, at temperatures that would kill an unprotected worker in minutes, a single locomotive hauls cargo through the longest railway tunnel ever built, the Gotthard Base Tunnel, officially opened in 2016 after 17 years of continuous excavation. And here's where it gets extraordinary. When engineers bored from both ends of this 57-kilometer passage and met underground in 2011, they were off by just 8 centimeters vertically. 8 centimeters. To put that in perspective, that's the precision required when drilling through a mountain for nearly 36 miles in the dark. But here's the question. How do you even plan a project this audacious? How do you move 28.2 million tons of rock, that's 5 Great Pyramids of stone, through a mountain while managing temperatures hot enough to melt steel? Geological zones so unstable they defy traditional tunnel boring methods, and the constant threat that the entire mountain could collapse on your head? The answer reveals one of the most ambitious engineering stories of the 21st century. For 800 years, the Gotthard Pass has been the gateway between northern and southern Europe. Trade routes, armies, merchants, refugees, everyone who needed to move goods or people across the Alps came through here. In summer, it was a few days' journey. In winter, impossible. The pass closes. The mountains win. By the 1980s, the problem wasn't snow, it was trucks, thousands of them. The Gotthard Road Tunnel opened in 1980, and suddenly the mountain was carrying more freight than ever before. But the old rail tunnel, built in 1882, was at capacity by 2013. The infrastructure couldn't keep up with Europe's demands. And then there were the accidents. The Mont Blanc tunnel fire in 1999, the Gotthard Road Tunnel disasters, hundreds of deaths from crashes, collisions, and fires in confined spaces. These weren't abstract problems for Switzerland. They were headlines. They were families. And they forced a question: is there a better way? In 1992, Swiss voters said yes. They approved the new railway link through the Alps, the NRLA, an entirely new tunnel. Lower, flatter, stronger. It would cut the Zurich-Milan journey by 1 hour. It would shift cargo from trucks to trains, removing dangerous freight from mountain roads and reducing emissions across an entire continent. But first, you had to drill through a mountain that didn't want to be drilled. Sortiment, become. The Gotthard Massif isn't just a mountain. It's an ancient geological fortress. Granite, gneiss, slate. Rock types that have been compressed and tortured by tectonic forces for hundreds of millions of years. And buried within it are zones called calcarite, crushed rock that's too unstable for standard tunnel boring. This was a problem no engineer had truly solved before. There was no precedent, no playbook. The overburden, the weight of the mountain above, exceeded 800 meters in some sections. Beyond that, you enter territory where rock pressure becomes almost unimaginable and temperatures climb to 45 degrees Celsius in unventilated chambers. So the project managers made a radical decision. Don't drill from one end. Drill from 5. 5 access shafts, 5 construction sites, each boring toward the other simultaneously. This approach meant shorter individual segments, more manageable, less risky, but it also meant 5 different teams had to coordinate, drill, and somehow meet underground with millimeter precision. They used 4 Herrenknecht gripper tunnel boring machines, the most advanced TBMs ever built for this application. Each one was the length of 4 football fields laid end to end. Each weighed 2,700 tons. Each cost around $21 million, and each was composed of 90,000 individual parts. But here's what's truly mind-bending. These machines didn't just carve a tunnel. They sensed what was ahead. Using probe drilling, seismic imaging, and water detection systems, the TBMs literally listened to the rock ahead of them. If they detected dangerous zones, water-saturated rock, fault lines, calcarite chambers, they could adapt their approach in real time. Slow down, inject concrete, reinforce. This wasn't mechanical drilling. This was intelligent drilling. At peak operations, 2,400 workers operated across 5 sites, split into 3 shifts, working 24 hours a day for more than a decade. They laid 290 kilometers of railway, enough to reach from London to Paris. They set 380,000 individual sleepers. They installed 500 kilometers of drain pipes, and they excavated 28.2 million tons of rock. That material wasn't wasted. 90% was recycled and reused, ground into concrete that was cast back into the tunnel itself, creating a kind of geological regeneration. Then came October 15, 2010, the moment that every tunneling engineer dreams about and fears. The Eastern Tube breakthrough. One machine bored through to meet the other. Champagne. Tears. The mountain was finally opened. Months later, the Western Tube broke through. 2 tubes, 57 kilometers long, converged with an accuracy of just 4 millimeters horizontally and 8 centimeters vertically. If you extended that precision to the distance from New York to Los Angeles, the margin of error would still be undetectable to the human eye. And if engineering like this captivates you, if the idea of pushing the absolute limits of what's possible fascinates you, then hit that subscribe button. There are more stories like this waiting. Shah could be June 1st, 2016. The tunnel officially opened. The journey from Zurich to Milan, 2 of Europe's most important commercial hubs, instantly became 1 hour faster. What used to take nearly 4 hours now takes 2 hours and 40 minutes. From Lucerne to Bellinzona, 45 minutes shaved off. But numbers alone don't capture the real transformation. The tunnel can carry 260 freight trains and 65 passenger trains every single day. That's nearly 330 trains traveling simultaneously through the same 57-kilometer passage. Each freight train carries cargo that, before the base tunnel, would have required dozens of trucks on dangerous mountain roads. Fewer trucks means fewer accidents. Fewer accidents means saved lives. And it means less CO2 pumped into the atmosphere, because trains powered by electricity are exponentially more efficient than diesel-burning freight vehicles. The tunnel transformed Switzerland from an obstacle into a gateway. Trade between Northern and Southern Europe didn't just get faster, it got cheaper, safer, and cleaner. Yet the story doesn't end with triumph. On August 10, 2023, a Swiss Federal Railways freight train derailed inside the Gotthard Base Tunnel. The world's most advanced railway tunnel, the one that had survived a decade of construction in the most extreme conditions, suddenly failed. Not because of the engineering, but because of a single broken wheel, a component so small it would fit in your hand. The tunnel closed. Alpine rail freight rerouted. 13 months of disruption, hundreds of millions in economic impact. It was a humbling reminder that even the most extraordinary engineering is only as strong as its weakest component. And in a system carrying hundreds of trains daily beneath 2.3 kilometers of rock, there's no such thing as insignificant maintenance. The tunnel reopened, inspections intensified, and now construction has begun on a second base tunnel scheduled to complete in 2027. Redundancy, backup systems. Because when you've built something this important, you can't afford for it to be the only way through. The Gotthard Base Tunnel is a triumph of precision, persistence, and problem solving. It moved 28 million tons of rock. It employed thousands. It cost $12.2 billion and took 17 years. But here's what makes it truly remarkable. It proved that the impossible, accurately meeting 2 drilling teams in the dark after 57 kilometers of excavation, becomes possible when you combine cutting-edge technology with extraordinary human determination. And yet, that 2023 derailment asks a harder question. We can drill through mountains with millimeter precision. We can move mountains of rock and rebuild them as concrete. We can synchronize 5 construction sites across a decade. But can we guarantee the safety of 330 trains a day, every single day for the next century, beneath 2.3 kilometers of alpine rock? What do you think? Would you trust that answer? Drop your thoughts in the comments below. And if you want to see more stories about the structures that hold our world together, the engineering that pushes the limits of what we thought possible, hit that subscribe button and turn on notifications. We publish new documentaries every week, and you won't want to miss them. Thanks for watching Titan Structures. See you next time.